Problem F713. Draw the shear and moment diagrams for the beam. Now, we could do this as an estimate by hand, and the textbook goes into how you can do this. I don't really like doing it this way because it is very easy to forget something when you're trying to look at all of the things that are affecting this beam. So my preferred way, and the way that you will need to do for some of these problems, is to find the force, the shear, and moment functions, and then graph those. So consider this beam right here. There are 3 downward applied forces. We also imagine there's going to be reactions at A. And this is a firmly connected support. So there's potentially reactions in the X, reactions in the Y, and an applied moment at the beam. Now I'm going to start off saying there's nothing else happening in the X direction. Reaction in X is 0. So that means all we need left is reaction in Y and moment. So we take our Newton's second law equations. So for sum of forces, we say there's 4 kilonewtons down here, 6 kilonewtons down here, 8 kilonewtons down here. And this reaction force, I'm going to say it's up at A. Next, we want to use the sum of moments equation. I'm going to select point B so that the force or reaction at B, or at A, is not going to affect this. So these 3 each create reactions, and they will each create they will each create moment in the positive direction. So this will create 4 kilonewtons times 3 meters, 6 kilonewtons times 2 meters, and 8 kilometers times 1 meter, plus the reaction moment at A. Put these 2 formulas together, or even solve them separately, we can see that the reaction force at A is 18 kilonewtons upward, and the reaction moment at A is 32 kilonewton meters in the clockwise direction. So that should be negative. Now, for shear force, to create the shear function, we're going to start on the left, and this is what we always do. We start on the left-hand side of the beam, and if there's no force on the extreme left point, that initial shear force is 0. However, because there is this 4 kilonewtons applied there, we can say that the shear function from here to here is 4 kilonewtons. It's 4 kilonewtons so that no matter where we cut it in here, that's enough to support this 4 kilonewton force. Same thing between here and here. Wherever we cut it, we would need 10 kilonewtons upward. And between here and here, we would need 18 kilonewtons upward. So the shear function, we'll define it as a piecewise function, is given by this formula. And as we can see, the shear function, when we approach the support, is 18 kilonewtons, plus 18 kilonewtons gets back to 0. Now our moment function, we need to consider that the shear represents the derivative of moment. So to find the moment function, we're going to start, again, say at the leftmost point it's 0. There's no applied moment at this point, so we can say that. So the moment at the leftmost point is 0. Then we're going to say that moment is equal to the integral of shear. But shear is a piecewise function, so we need to do a piecewise integration. So for the first piece, moment of x is equal to 0, which is the moment at the point that it starts. It starts at 0, goes up to x. The shear function is negative 4 kilonewtons, so the integral of negative 4 kilonewtons dx is negative 4 kilonewtons x. And this one's easy enough because we go from 0 to x, so that's easy. So the moment function, at least for that first segment of the beam, is negative 4 kilonewtons x. Now, if we evaluate it right here at the breaking point, where the point where the 2 pieces of the function meet, plug in x equals 1 meter, and we get that the moment at 1 meter is negative 4 kilonewton meters. For this second segment of the beam, between here and here, we're integrating starting from this point. So we need to say it starts at -4 kilonewton meters, plus the integral from, and we start at x equals 1 meter to our variable position. And in this region, the shear function is -10 kilonewtons. So that's -4 kilonewton meters plus the integral from 1 meters to x of -10 kilonewton dx. -10 kilonewton dx, the indefinite integral is -10 kilonewton x, evaluated from 1 meter to x. So -4 kilonewton meters plus we plug in x for here, -10 kilonewton x. Then we plug in 1 meter and subtract it. And the net result, because we can combine these two terms, is that the moment function in the beam is equal to 6 kilonewton meters minus 10 kilonewtons x, for x is between 1 meter and 2 meters. One more. To solve for this next part of the beam, we need to know the internal moment that it starts at. So we plug in 2 meters into this function. 6 minus 10 times 2 is -14 kilonewton meters. So the moment in the third segment of the beam starts at -14 kilonewton meters, plus the integral from its starting point of 2 meters to the variable x of, this time the shear is -18 kilonewtons, so -18 kilonewtons dx. We can evaluate this integral as I do here. And so for the third part of the beam, we get 22 kilonewton meters minus 18 kilonewton x. Now, the question asks, draw these functions. So one thing we could do, we could try to freehand this. We could say, well, this is obviously a step function. So it starts off at -4 for a meter, then -10 for a meter, then -18 for a meter. And you should get something that looks like this. The moment function is a little more complicated, but it is saved by a couple things. First of all, since there are no applied moments to the beam, there will be no discontinuous jumps. So the moment function will be continuous, not necessarily smooth, but continuous. In fact, because shear is the derivative of moment, we can see, okay, shear is constant here, it's constant here, it's constant here. The moment graph is going to be composed of a set of straight lines. It's going to be reasonably shallow for the first meter, steeper for the second meter, and even steeper still for the third meter. We could also, because we recognize that the moment function is composed of straight lines, could find these points. Moment of 0 is 0, moment of 1 meter is -4, moment of 2 meters is -14, and moment of, well, if you plug in 3 meters for here, you would get -32. Wait, I already calculated this. You would get, yeah, -32. So you could play connect the dots there. This will not always work, and you might not want to rely on your ability to hand draw graphs, in which case you can draw these graphs using a spreadsheet program. The program that I prefer is Google Sheets, but you can do this in Excel as well, and I'm pretty sure Apple has their form of it. I just don't know what it is offhand. But to do this, we need our functions, both shear and moment functions. So here is the sheet that I used to make this. So first, x. I arbitrarily selected points that were 0.1 meter apart from each other. And the way you can do this really easily is start off, first value is 0, and then the value below it is equal to, so here I'll go ahead and do this out while you watch. Start off with equal to let it know that it's going to be a formula. Click on the cell above it to say I want the cell above it plus 0.1, and it will calculate that out. And then you can, at least in Google Sheets, and I know this is also true in Excel, you can click on this lower right-hand corner, there's a blue square, drag it down, and it will copy that formula, but not that formula exactly. It will copy the relationship. So notice how this one is the cell above it plus 0.1. Well, this is the cell above that plus 0.1, the cell above that plus 0.1, etc. Now, you might notice I didn't do that for everything, and that's because we can't, in order to do a discontinuous jump like this, you actually need to have the same x value twice. So I recognize that there is going to be a discontinuous jump in the shear function at x equals 1 meters and x equals 2 meters. So I had 1 meter and 2 meter done twice. Now for v of x, I did not calculate, well, actually for this one I did. V of x for the first segment was -4. For the second segment it was -10, and the third segment it was -18. And then I also said because of the reaction at A, it jumped up to 0, but that's not really that important. Now for moment of x, I did not individually calculate all of these. I used the function because I do have a moment function. So the moment function for the first meter was -4 kilonewtons x. So the formula is -4 times x. Now that is true up until here. We made the sudden discontinuous jump, so I changed the formula. For the second part, it's 6 minus 10x. So 6 minus 10x. And then I made the new jump here, 22 minus 18x. And so you have your three columns: x, shear of x, and moment of x. You can go ahead and make your graphs out of those.